Chapter 6, number 37. 3 boxes of masses m, 2m, and 3m are connected as shown in the figure below. A force is applied to accelerate the boxes toward the right. Rank the tension in the ropes T1, T2, and T3 from smallest to largest when the boxes are in motion and there is no friction, and then the same thing when they're in motion and there is a coefficient of kinetic friction mu sub k. And what we'll see pretty quickly here is that intuitively, T3 has to be more than T2, which has to be more than T1. The reason for that is that T3 needs to essentially accelerate the entire collection of things. So it has to accelerate all 3 boxes. They're going to all have the same acceleration, but then T2 only has to be, this is T3, T2 only has to accelerate the inner ones, and T1 only has to accelerate this box. So in essence, what we'll end up getting is that if they have a combined acceleration, or if they each have an acceleration of a, and because they're connected by ideal strings, they have to have the same acceleration, then it will turn out that T3 is the sum of their masses times A, but T2 is only its included masses times A, and T1 is just going to be the leftmost mass times A. Because if we consider them as combined systems, those are the objects that are being accelerated. If the intuition there sort of leaves you cold, we can actually show it, so we'll do that. But this is the end of the problem. But if you want to see it sort of shown algebraically, I'll do that next. So let's draw the free body diagrams. We're going to ignore the vertical forces, the weight and the normal, because they're going to cancel out. And yes, they would play a role in the friction, but the friction will just be the same mu k times those normals, and will all scale the same way. So will not be, strictly speaking, very relevant. And then we have T3 pulling to the right, and we know that there's a tension connecting in the rope connecting the 3m to the 2m, and that's T2. It pulls the 3m backward, but it pulls the 2m forward. And in the same kind of reasoning, this tension between 1 and 2 pulls the 2 backward, but pulls the 1 forward. And as pointed out before, they all have the same acceleration A. So from the free body diagrams, the sum of the forces on block 1 is T1, and the sum of the block forces on block 2 is T2 minus T1, and the sum of the forces on 3 is T3 minus T2. And then from Newton's second law, the sum of the forces on 1 is ma, and the sum of the forces on 2 is 2m times a, and the sum of the forces on 3 is 3m times a. And in this configuration, when we're talking about each individual block separately, we have to use their separate masses, the m, 2m, and 3m, instead of considering them all one object, in which case the tensions would have canceled, and we'd have just the mass 6m. All right, and then we just put these things together. So we say that T1 equals ma, and that T2 minus T1 equals 2ma, and that T3 minus T2 equals 3ma. We can then take this result and put it in here to give us T2 minus ma equals 2ma, meaning T2 equals 3ma. And we take that result and put it up here, and we have T3 minus 3ma equals 3ma, or T3 equals 6 MA. So as promised, T3 is bigger than T2 is bigger than T1. So how about if there is friction? If there's friction, we need to add some things back in. For instance, then we have to worry about there being a weight, which is mg, or 2mg, or 3mg. We have to worry about there being normal forces, so an Fn3, and an Fn2, and an Fn1, because we also know that it's going to be a frictional force, which I might call like F1, and F2, and F3, which makes life more annoying, but not actually that much harder. Our first thing, which we can just see, is each of the normal forces is just going to be the appropriate weight, because we still have no vertical accelerations. So without further illustration or proof, we're going to essentially jump to the idea that Fn1 is mg, and Fn2 is 2mg, and Fn3 is 3mg. And then we know that the frictional forces are going to be mu times the normal force, because it's kinetic, and that's always the same. Which allows us to say the frictional force is actually just going to be mu mg in the first case, and 2 mu mg in the second case, and 3 mu mg in the third case. But now we want to go back and say, well, from our free body diagram, now we have that the sum of the forces on 1 in the x direction, but is T1 minus FF1, and the sum of the forces on 2 is now T2 minus T1 minus FF2, and the sum of the forces on block 3 is T3 minus T2 minus FF3. And we know from Newton's second law that the sum of the forces on 1 is just ma, and the sum of the forces on 2 is 2m times a, and the sum of the forces on 3 is 3m times a. So that's getting a little messy, but not too bad. So we can put these things together, and we can say, well, that says us that T1 minus mu mg equals ma. So T1 equals ma plus mu mg. And we put that into this equation, and we get that T2 minus T1 minus 2 mu mg equals 2ma. So T2 minus, and we have that this was ma plus mu mg, plus minus, 2 mu mg equals 2ma, and therefore T2 equals 3ma plus 3 mu mg. And something similar is going to happen for block 3, but I'm sort of out of room, so I have to go to a different screen. We would have T3 minus T2 minus 3 mu mg equals 3m times a. So T3 minus 3ma minus 3 mu mg minus 3 mu mg equals 3ma. Or T3 minus 3ma minus 6 mu mg equals 3ma. And then we'd add everybody to the other side, so we're going to add plus 3ma and plus 6 mu mg over to here, 3ma plus 6 mu mg, and I'm left with T3 equals 6ma plus 6 mu mg. And once again, we have T3 is greater than T2 is greater than T1, as promised.